Welcome back to the series of lectures on high-performance scientific computing. In this video, we will talk a little bit about programming for multiple device architectures with OpenACC, with OpenMP and OpenACC, with MPI and OpenACC, and we will also check how these concepts scale to very large and multi-node systems. First, we have to look at what is multi-device architecture. So typically, sometimes you have multiple devices on a single machine. So far, whenever we used directive-based programming or any other direct form of programming, we just programmed for a single device. However, there are many machines that contain more than one device. For example, it is very common that you have a machine with multiple GPUs. So in this video, we will now discuss how to implement multi-device programming in several different ways. In order to utilize multiple devices, we have three options. We can queue up multiple device operations using the OpenACC built-in functions and async clauses, which we studied in the last video. We can use OpenMP threads and assign each of it to a separate device. We can also use MPI and assign each MPI rank a separate device. First, we will now discuss multi-device programming with OpenACC only. To utilize multiple devices with OpenACC, we will need to use some built-in functions to the OpenACC specification. We will also need to use some of the concepts from OpenACC asynchronous programming. First, we need to figure out what are the number of available devices. So you need to use a function ACC get num devices. Each device on the machine will be now assigned a unique number and ID. For example, in this frame, you can see that there are multiple GPUs, each of it being a Tesla K20X. Now, each different Tesla card is assigned a unique ID starting from the number 0. And we will now use the number of available devices to split up the computational work between them. So we need to change, if you need to change the active device, we can say ACC set device num, and then we can now give, this function will then switch the active device. By using this function, we will be able to queue up a device operation and then switch to another device. By marking a loop as async, the code is able to move the next loop and launch it on a separate device without waiting for the first loop to finish. We must ensure that we have independency of data over here. Let's revisit the program of the Mandelbrot set. We had divided the Mandelbrot set image into 4 blocks. Now, to demonstrate the different methods of multi-device programming, we will use these 4 blocks. Our goal, obviously, within this code is to compute each of these blocks on a separate device. First, we will walk this through a pure OpenACC approach. We need to allocate the memory ahead of time because allocation, deallocation does not always work synchronously. We also want to avoid allocating the entire array on each device just because we do not need to. So first, we loop over all devices. We launch the compute asynchronously. Then we launch the data transfer asynchronously, and then we continue on to the next device. So we are doing this device by device. And then finally, we have to deallocate the data. So when we are using async for multiple devices, each device will have separate async queues. So when we have Pragma ACC parallel loop async, each device will use its own default async queue automatically. Lastly, when using multiple devices, we will have to do a little bit of extra work to ensure that all devices finish before moving on with the other bits of the code. If you use a single weight, it is not able to cover all the devices. So for multi-devices, we need to loop over each device and tell it to individually wait. So if you just issue a hash pragma ACC wait, it's not going to do it for multiple devices. Each and every device has to be individually told to wait. How do we do multi-device with OpenMP now? So in OpenMP, we will assign each of our devices to an OpenMP thread. So for example, if there are multi-core CPUs and you launch 4 OpenMP threads, each OpenMP thread now becomes a particular device. This will allow us to utilize multiple devices similar as before without needing to use the async clause. You're also able to assign multiple threads to the same device, but it might not be advantageous because you cannot fully utilize the device with a single thread. So you have n devices. We loop over all of our available devices like before. However, now we break them among OpenMP threads. Each thread will utilize its own device. No async is required for the OpenMP variation, but it still helps to keep it because this will be useful when you're using it later. So if you look at the Mandelbrot set now, first we parallelize over the outer loop with OpenMP. We assign each thread to a different device. And then since OpenMP is a shared memory model, all threads can copy their output immediately to the same array without any issues. How do we achieve multiple devices with MPI? MPI is a little bit more difficult to implement. The reason is it has a communications library within itself and it is inherently designed for distributed memory architecture. If you remember that there is no shared memory with MPI and any data needs to be explicitly sort of computed. So while it is more difficult to implement, it is generally more flexible and it is very scalable. So in the last 2 programming models we covered, it did not behave differently from what we expect from OpenACC by itself. However, if you look at an MPI plus OpenACC code, it will look more like a standard MPI code with some sort of OpenACC directives introduced. You will still have to do the things of initializing MPI. You need to get the communication size. You need to get what the MPI ranks are. And now what it essentially means is that each rank will now run on a different portion of the loop or different loops entirely. When using multiple devices, we can assign each MPI rank its own device. These ranks could also share devices if the device is being underutilized. Now, if you want to break up the MPI, the Mandelbrot program using MPI, we will now have to initialize the MPI, and because it uses distributed memory, each rank will now compute only its subimage. You have to explicitly transfer that data, and then at the end, you have to gather all the subimages and put it back together using the MPI gather function. Because each MPI rank uses a different device, it is based on its rank number. We will also alter the value of y based on rank since each MPI rank needs to only compute its own portion of the image. And that's where you do it in this subimage bit of code. You also have to facilitate device-to-device data transfer using the host data directive and the use device clause. And we need to pass device pointers using the MPI gather call. This should move the data from device to device if the architecture is able to. For example, we can use the OpenACC host data use device to move data directly between devices using the pragma function over here. If you want to do host data transfer with MPI from one rank to another rank, we have to use the classic MPI send and then the corresponding MPI receive in rank 1. So if you're sending data from say rank 0 to rank 1, so you have to now use the device array and then use device, do an MPI send. Now let us look how the multi-device optimized Mandelbrot looks. So the Mandelbrot set is now divided into 4 devices, 0 through 1. As a final example, we want to re-implement the async optimizations from the previous module to our multi-device setup. We will use OpenMP to break up the work among multiple devices, and we will use OpenACC async to optimize the code further on each device. So in the multi-device mode, without having async, device 0 would do one part of the block, say let's say block 0 and block 1, then do the data transfer. First it will do block 0, then do the data transfer, then block 1, then the data transfer. And then device 1 will do block 2, data transfer, block 3, then the data transfer. If you use multiple devices and async, we are able to interleave the compute of we are able to interleave the computation of block 1 with the data update of block 0. Similarly, on device 1, we are able to interleave the update of block 2 with the compute of block 3, which will enable us to finish faster. So if you look at the finished Mandelbrot program, you will now again have 2 asynchronous blocks for the OpenACC parallel bit of it between block 0 and block 1. So each device is now further divided into 2 blocks. We can also do extremely large scale OpenACC. So in this module, so far we have focused on programming for a single machine, which is commonly known as a node. Some computer applications are run across many nodes, sometimes upwards of hundreds of thousands of such nodes. Typically in large supercomputers we have at least close to 100,000 such nodes. On top of this, each node could have one or more accelerator device, like a computer having multiple GPUs, and in some cases multiple CPUs as well. So with MPI and OpenACC, we can program for this extremely large-scale multi-node, multi-device architecture. So when you have multiple nodes and multiple devices, you can see this is essentially the sort of diagram that you have. You have a CPU, which high-capacity memory, which is now connected to 2 devices on node 0. And through some sort of a network, you have another node 1, which is identical to node 0, again connected to multiple devices. And this is where you will start to exploit the parallelism. So in order for your program to work in this style of architecture, you would be using MPI to manage essentially the node-to-node communication. But you will also use OpenACC to accelerate the code on each of these devices on each of these individual nodes. With such a large architecture, you will need a good understanding of both MPI and OpenACC. All of the concepts that we have discussed with OpenMPI and with OpenACC would apply over here. So what is the takeaways from this session? Overall, for multi-device programming, each method obviously has its pros and cons. Using OpenACC async and OpenMP plus OpenACC are both good for utilizing one node which has multiple devices. Think about it as having a multi-core CPU with multiple GPUs. Then having OpenMP plus OpenACC is very useful. If you use MPI plus OpenACC, it might be very hard to program, but this will allow the application to scale across extremely large number of devices. And typically most modern supercomputers are configured in this way. It also takes away the restrictions on the total maximum number of CPU cores that you'll be able to use, because then you are no longer restricted to shared memory machines. You can now use distributed memory machines. Depending on the kind of science that you're doing and what is comfortable for you, your use case would decide which method you would like to do. If your problem requires millions of processors, then it is better to do MPI plus OpenACC and take the time and effort for doing that. Thank you.